All right, so hello. So I'm just curious, is this Miss or Mr. Michael Alpha?
Sir Miss po.
I see. Michael is the name of a guy. Alpha
Sir,
is also,
apelyado ko po yung Michael.
yeah. So I dropped those two. So Michael, Alpha, tapos Ray, parang lahat pang lalaki. Kaya,
Somehow.
am I the only one who mistook you as a guy? If it's just a name, okay. Pag pangalan lang, kasi pag mukha talaga, sasabi mo ng babae kagad.
Ikaw lang
Or
yata, sir.
wala. Well, that's because you don't have a picture, okay? So I don't know if you're a guy or a
Sige,
female.
sir, maglalagay na.
Anyway, so let's now continue our solutions with your quizzes. So for the quiz discussion number 8, so we have this parallel part or connection. So this one is actually super simple. Just get or combine those two and then make it, in one resistance. Okay, and then you'll be having a series connection already. So from there, you'll be having an easier way for you to be able to get the I total, R total, I sub 1, I sub 2, I sub 3, and so on and so forth. So here's the solution of Miss Michael. So for the total resistance, so just add the, I need, oops. All right, so wait a second. I just need the circuit diagram. So messy. Ito na pala yun. Where is our solutions? There you go. So from here, for you to be able to get the R total, just put this one on the other side. Okay. For you to be able to get the R total, so just add the R1 and R4 first, and then get the combined, okay, or the parallel uh, output of the R2 and R3, wherein it could be something like this. So 1 divided by 1 over 8 plus 1 over 8. Okay. And then plus 5 ohms for the R1 and then plus 6 ohms for the R4. So just use your calculator and then you will get 15 ohms. For the total current, since you already have the R total, then that's the time that you can now perform. Let me just make this one bigger. So that's time that you can now perform this one. So V divided by RT. So 60 volts as your total voltage and 15 ohms as your total resistance. Okay. And you'll get 4 amps as your total resistance. And then for the I1, so I1 is actually equal to I4 since they are in series connection. So that's the rule in series. And we have here I2 is also equal with I3 since you're going to have one flow of current since you have already combined the I2 and R3. So whatever is the current flowing on your I2 will be the same that is flowing on your I3. Okay, so just get the combined value of your R2 and 3, which is 1 in here. So 12, no, not 1. So 1 divided by 1 over 8. So he didn't get the calculated value of this one, but he'd still get the entire expression. So in here, just perform this one, and then you will get 12 divided by 4 or 3 amps, okay, as your current on the R2 and R3. And then for the voltage drop, so this one is super simple already. So just get the individual resistance multiplied to your I total. Okay, and then of course, yeah, everything is I total. Then of course, just get multiply it to the individual resistance. So 4 times 5, you'll get 20 volts. 4 times whatever is the result of this one, you will get 12 volts. So right here, 4 times 3. And then 4 times 6 will give you 24 volts. All right. And what else? So this is for the number 8. And then for the number 9, so I guess this one is super simple, super easy since this one is series connection. So I will not explain this one anymore. But the answer on the R total is 18 and the I total is 0.67 ohms. And then for the last one, so in here, there is the, okay, so we don't need that one anymore. So in here, for you to be able to get the R total, just apply this one, okay? 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3. And then for the I total, so as long as you have already, as long as you have the correct answer for the R total, then you can now compute for the I total. So I is equal to V divided by R. And then for the current, so just get their individual voltages, wherein VR1 and VR2 and VR3 is of course equal to 125. Okay, so performing the I1, I2, and I3 will now be depending on the resistance, okay, below them. So I1 is equal to V1 divided by R1, okay, and then I2 is equal to V2 divided by R2. So just do that one, and then you'll be able to get those results: 6.25, 1.25, and then 2.5. And then for V1 and up to V3, so this one is already a bonus since it's in parallel. So the voltage across here is 125, 125, and then 125. All right. And then for the P1, so just get the individual current. Okay. Current for the I1, current for the I2, and then current for the I3. And then you will get this one. So all of them will be multiplied to 125 volts. Okay. So yeah. So that's it for your quiz number 1. So any questions so far? So it took us longer than I thought. So any clarification so far? So where is that part that you guys would like to see when it comes to your quiz? So that we can go over on that one again, and then let's see whether you've got the incorrect process or solution so that we can compare. Anyone? So I'll count 5 seconds. If no one will speak, then we'll start with our discussion now. So 5, 4, 3, 2, and 1. Okay, so no question so far regarding with your quiz. Hello? You guys still there?
Sir, wala pa naman po.
Wala pa, sir.
All right. Okay, so if there is no question anymore, then let's now proceed with the module 4. So module 4, I have already opened that one. All right. So let us now start with module 4. So Maxwell's loop, or sometimes just call this one mesh. Okay, current method. Okay, so this one is invented or came or idea by James Clerk Maxwell. So as you guys can see, it came from his last name. So his idea is widely used in circuit analysis technique, especially if you have a much more complicated circuit. Okay, so let's just say that Maxwell loop current method is much more better to use than the Kirchhoff's law. So yeah, Kirchhoff's law is also useful. However, if I will compare this one with the Kirchhoff's law, using Maxwell is a lot more easier. Okay, why? Because you'll have lesser equations. Unlike in Kirchhoff's law, you'll have more equations to solve. But in here, you'll have lesser equations. So this idea in Maxwell loop current method, so we identify all the meshes of the circuit. So that's why it's called mesh. Okay, so we are the one who's going to assume the flow of current. Okay, how does it work, or how or where will the currents will go to? So imagine one loop current for every mesh, and then the direction of the loop currents may be arbitrary. But generally, we consider co-directional loops currents for the shape of our calculations only. Okay, so in here, this one is actually quite similar with the branch current method. Okay, so branch current method is the one that is being used in Kirchhoff's law. And it uses simultaneous equation. So we have already performed this one. Okay, last meeting, with one of our example. Okay, so the one that we did last meeting is called the branch current method. Okay, if we're going to solve for a specific variable with the use of simultaneous equations. So yeah, Kirchhoff's voltage law and Ohm's law is significant when it comes to branch current method. Okay, so we use that one to determine the unknown currents in a network. So as you guys can see, from the foundations, from the Ohm's law up to the KVL, so you'll be able to apply those in mesh current method, okay, or Maxwell current method. So that is why if you haven't fully understand Kirchhoff yet, Kirchhoff's law, so I encourage you to practice, okay, practice more and more and more until you can master it. And then performing Maxwell loop current method is just super easy to you, okay, once you have mastered that one. Since we apply what we have learned in Ohm's law and in Kirchhoff's law here in Maxwell current method. Okay, so in here, the only difference of the Kirchhoff's law to the Maxwell, okay, or mesh current method is it does not use Kirchhoff's current law. Okay, so yes, we still use Kirchhoff's voltage law, KVL, but we don't use KCL anymore in Maxwell. If you're going to use KCL, then that is not Maxwell, or that is not mesh current method anymore. That is already Kirchhoff's law. Okay, so in here, we use a different thing. Okay, so or just by purely Kirchhoff's voltage law. Okay, so this one is usually available to solve a circuit with less unknown variables and less simultaneous equations. Okay, which is of course especially nice if you're forced to solve without a calculator. Okay, so instead of having 5 equations, you're only going to have 3 equations when it comes to Maxwell's loop. So here's one example. So let's see how this method works on this example problem. So we have a voltage source in here, and then another voltage source in here. Then of course we have 3 resistors. Okay, 4 ohms, 2 ohms, and then 1 ohm. So the first step that you need to do is identify the loops. So basically, they are the same when it comes to the process of Kirchhoff's law. So we have to identify the flow of current. So in my case, I always go with positive key or conventional flow of current. So in here, we'll be having a clockwise, okay, clockwise flow of current or clockwise loop, right? So it's from left to right. And then on the right side, okay, so this is another loop wherein I always go with positive. Okay, so in here, we have here a counterclockwise flow of current. So it's from positive to negative. Okay, so it's always the one that I'm using. Okay, I don't use the electron flow method. I always use the conventional method. All right, so from here, we'll be able to form the B1, R1, and R2 for the first loop right here, and then B2, R2, and R3 for the second loop. And what else? So it says here that in fact this method gets its name from the idea of these currents meshing together between loops like sets of spinning gears. Okay, so depending on the flow that you have assumed. So in here, we have here a first loop, which is spinning clockwise, and then second loop, which is spinning counterclockwise. All right. So the choice of each current's direction is entirely arbitrary. Okay, so just as in the branch current method, but the resulting equations are easier to solve if the currents are going the same direction. Okay, through the intersecting components. So mostly, we'll be having a the same flow of current on the intersection part. So where is that intersection part? So it's the R2, okay, or this branch. So as you guys can see, if we are going to assume the flow of currents, so right here, I have this circuit or this current flowing, and then right here, we also have at this point. So upon reaching this node, so they will meet right here, and then we'll go down on our R2. Okay, so in that case, it's a lot more simple and much more better if we have the same flow of current on the intersection. Why? That is because most of the time, if we have the same flow of current on the intersection, so you won't be having any problem whether you get the correct assumption of the let's say rotation of the current or no. That's because if you have, let's say, negative result, then you have to go back on the start and then check whether this is really the flow of current. Because sometimes, even though you've got negative, you cannot just make it positive. Okay. So yeah, there are some cases like that wherein you got the incorrect answer. Okay. So you're lucky enough if the result of your, let's say, total current is positive. So always go with positive. If we have negative, just do it again. Okay, just change the flow of the current. And then if you've got the same value, then maybe the answer that you've got is correct. Okay, so in here, it's better to have the same flow of current on the intersection part. Okay, so that they will just add up with each other. All right. So yeah, just note how currents I1 and I2 are both going up through resistor R2 where they mesh or intersect. So if the assumed direction of a mesh current is wrong, the answer of that current will have a negative value. So yeah, but sometimes again, if you get a negative value, 50-50. So it's not sure yet. Okay, we are not sure yet if you really get the correct answer or no. Okay, so just do it again and then get the positive value instead of the negative one. All right, so the second step after drawing the loop, then you must now label all the voltage drop of your circuit. Okay, so from here, okay, starting from your loop one, so we have here a positive and then negative, right? So I always go with the last sign. Okay, so since this one is R1, so this one will have some voltage drop. So this one should be positive, negative. Okay, so don't uh, make a mistake on this one. Okay, so avoid doing like this one is negative and then positive. Okay, So it's only natural that you will have a voltage drop on every resistors. So that is why the correct sign of this one is positive and the negative. So that if you're going to have this flow of current, so we have a positive source and then a negative voltage drop on the side. Okay, so I always get the last sign. So from here and then right here. Okay. And then another resistor here. So another voltage drop. So positive, negative. Okay. So that's how I label my components. And then for the B2, okay, or the second voltage source, so another voltage drop in here. So take note, it's flowing from right to left. So we have here positive, negative. So that if it's flowing on that direction, so we have a positive B sub 2 and then negative I2 times R3. All right. So were you guys able to follow so far on how I put my labels?
Yes, sir.
Okay.
Yes, sir.
So again, this is very, very important. Once you've made a mistake in putting a sign in here, like for example, you've just accidentally made this one positive and negative. So you're now adding another voltage source in here, which is supposedly not to be. Okay, so this is very important. So this one should be a voltage drop, not an additional voltage. Okay, and then from here another voltage drop since it will pass through another resistance. So negative and then positive. Okay, so another tip when it comes to super node or this intersection part, so it is always better to have this same signage. Okay, positive, positive, negative, negative. Because in that case, you won't be having any conflict, okay, with your results. So it's always 99% that you will always get the correct answer. All right, so that's how I label my loopings, wherein you'll have the same with this one. Okay, so what else? So yeah, so here are just some explanations. So this like right here, we will denote a resistors as a voltage drop, okay, as the product of resistance in ohms with respective with mesh current, that quantity being unknown at this point. Okay, so as always, if you're going to pass through a resistor, it's always a voltage drop, okay, not an additional voltage. Okay, and right here, so let's now start with the left loop. Okay, so starting from here for now, starting from the upper left one. All right, so we'll just have our own solution. I need more space. All right, so there you go. So from the loop one, okay, or yeah, loop one, we will be able to have this KVL equation, KVL at loop one. Okay, so from here I have positive B sub 1. What is the value of that one? So that's a 1 time big shift. Let me copy this one. All right, so from here we have positive 28 volts. Oops. Positive 28 volts. All right. And then for the second one, so it's negative. So I always consider the last sign. Okay. So once you've started considering this one, always just be consistent. Okay. So you must always get the last one. So if you started with the first symbol, then you must be consistent with the other components. Okay, so it should be the first symbol also. But in my case, I always get the last sign. So it's positive 28 minus I1 times R1. Okay, and then another resistor here, which is minus, okay, oops, minus I1 times R1. Sorry, R2. What is it I1? I2 times R2. But in here, there is another flow of current, okay, that will affect your R sub 2. So that is why in here, you have to change that one into R2 times the first current that is flowing in this one, which is I1, okay, oops, sorry, plus, not plus, plus minus, plus, sorry, it's addition, okay? So if they have the same flow of current, then that one is addition. So the negative symbol that we are now considering here is already this one, okay? Your negative R2. For the currents, it's addition. So I1 plus I2. Now, if we have different symbols, like for example, we have here negative and then the other one is positive, then that's the time that you have to change this one into I1 minus I2. All right, so that is why if we have a contradicting symbols in here in your intersecting part, that's where you will have a problem because you're not sure if that one is I2 minus I1 or I1 minus I2. So it could be those two, okay? And if this one is correct, then the other one is incorrect. If this one is incorrect, then the other one is correct. So this is a no-no when it comes to intersection. So that is why it is a lot better if they have the same symbols. Okay? So if they have the same symbols, the first one, okay, the one that we're trying to consider is negative, and then if they have the same symbol, the symbol that you're going to use is positive. Okay, I1 plus I sub equals to 0. Okay, so this is your equation number 1. All right. So are we clear with that one so far? So this is your equation number 1. Hello?
Clear naman, sir.
Yes, sir.
Okay
Yes,
naman,
sir.
sir.
Okay. So again, my only advice when it comes to mesh is to avoid having a different symbols with this one. Okay. So I'll just remove this one. So if they have the same symbol, then it's always plus. All right. Then the next one right here is just the simplification. So just distribute your -2 or your R2. Okay. So 28 minus -2 times I sub 1 times -2 I sub 2 minus 4 I sub 1. So from here, you can combine those 2 I sub 1. So -2 I sub 1 plus -4 I sub 1 will give you negative I sub 1. Okay. So here's now the simplified form of equation. Okay. So yeah, that's it already for the loop number 1. Moving on with loop number 2. So let us answer number 2, KVL at loop number 2. Okay, so from here we have positive 7 volts. Let's remove that V. And then we have here negative I2 times R3. Okay, and then we have here negative R2. Okay, R2. And then again, we have a current that is flowing on this side and then another current that is flowing on this side. So we have to consider those currents that is affecting that component. So in here, we'll have I1 plus I sub 2, since they have the same flow of current is equal to 0. So this is now your equation number 2. So from here, just simplify this one just like what we did right here, and then you will get 2I sub 1 plus 3I sub 2. All right, so it's just that I wasn't able to show the solution right here. But the simplification of this one from here will be like this. All right. So are we clear so far for the loop number 2?
Yes, sir.
Yes, sir.
So,
All right. So here's now the part wherein we'll be using the this one simultaneous equation, solving for the unknown. So we have here your loop 1, and then we have here your loop 2. So we've just arranged them. So we have 2I sub 1 and we have here for the loop number 2. So from here we can, so they are not aligned together. Let me just make this one bigger. All right, so I'll just write it down. So we have here 2I sub 1. Oops. That is 1. Okay, let me just check. Equals to 0. Wait, this is the... I see. All right, so this is the first equation, and then this is already a second equation. Okay, so let me just copy those two. That is y. And then from here, you can now perform a simultaneous equation, just like what we did last meeting. So from here, we can actually multiply the second equation by 2 for us to be able to get 6i. No, they are not arranged. Okay, let me just arrange this one. Negative 28 plus 6i sub 1 plus 2i sub 2. And then right here, we have negative 7 plus 2i sub 1 plus 3i sub 2. All right. And then from here, we can actually multiply this one, the second equation, by 2. By 3, sorry. Okay. So our aim is to us to be able to get 6i sub 1. So from here, we'll have negative 28 plus 6i sub 1 plus 2i sub 2. Let's go to 0. And then negative 21 plus 6i sub 1 plus 9i sub 2. Okay. So when performing simultaneous equation, your goal in here is to eliminate one unknown. Okay, so if we will perform subtraction in here, 6i sub 1 minus 6i sub 1 will be already cancelled. All right, and then from here, so negative 28 plus 21, so of course this one will become positive. So you will get negative 7 plus 2 minus 9. So you will have here negative 7i sub 2 is equal to 0. So from here, you can already perform this one. So transfer this one to the other side. So 7. And then you will have negative 7. So I sub 2 is equal to negative 1 amps. All right. So let's see. Yeah, negative 1 amps for the I sub 2. All right, so we don't have enough time again anymore. So we'll just continue the rest on the part 3. All right. So see you guys on part 3.
So, bye, sir.
Goodbye.